Welcome to Coursera's Instrumental Analysis class. I'm Vicki Colvin. This is lecture 7 in a series that we're doing at the beginning of the class on error and measurement. We've covered everything from significant figures through your sort of basic replicate measurements to using confident limits. And today what we're going to be talking about is combining different sources of error, because it's rare that whenever you do a measurement you only have a single error source. Usually there's error in the pan balance, there might be error associated with the instrument itself, and you need to combine or propagate these errors to come at an overall error for the reported data that you're putting out. So let's do the example of these cylinders. They're made of some metal, we don't know what, and our game plan is to measure the density of the metal and thereby figure out what it is. So we're going to need to weigh a cylinder, and we're going to need to also get its volume. So we might use a pan balance for the weight, maybe a graduated cylinder for the volume. But each of those two pieces of data will have an error, and in the absence of replicate measurements, we're going to take the tolerance of the pan balance as plus minus 0.01, and the graduated cylinder is interesting. If it's a large volume, you might be inaccurate. Here, I'm going to guess, based on my ability to use it, that I can tell where that meniscus is to plus or minus 0.05 mils. You could also choose to take the instrument tolerance. It's printed on the graduated cylinder, or you can, as I said, assign your own based on how well you personally can use it. So in that case, we can certainly know the sig figs are going to report out, but more importantly, how do we report the overall error in the density, because it's coming from two different places? Well, that's where we use the rules of error propagation, and they're pretty simple. If in your data analysis you're adding values, each of which has a spread, then to get the spread in the answer, you're going to take the square root of the sums of each of the errors, and that's going to give the error in the total. If, on the other hand, you're multiplying or dividing, as we're going to be in density, you need to convert all of your absolute errors to relative errors, and it's the same rule. You're going to square those relative errors, and you're going to take the square root to get the relative error of the ultimate result. So just remember, if you're adding and subtracting, you use absolute errors, and it's the squares, sum the squares and take the square root. And if it's multiplication and division you're doing, you're going to be using relative errors, again, which you're going to square, you're going to sum, and you're going to take the square root to get the overall error. So pretty straightforward equations to use. Let us go through a couple of examples. Let's take that example of the unknown metal rod. Say we measured the volume to be 50.3 mils, and we weighed it on an analytical balance, rather a pan balance, and found it 361 grams. What are the standard errors for volume and weight? What's the density with error, and what's the rod made of? Remember, use instrument tolerances to get at those errors if you didn't do replicate measurements. For graduated cylinders, I'll take plus or minus 0.2 mils. For analytical balance, I'll take 0.0005 grams. Now, you can have many different choices for these, and so the problem with instrument tolerances is I can't always tell you the right answer. It depends on the graduated cylinder. It depends on the balance, but I'm giving them to you in the measurement here. Now, density is defined as mass over volume, so this is going to be a multiplication division type of operation. So we are going to square the errors, add them together, and take the square root, but we have to be working with relative errors. So we need to convert our absolute errors that we get from tolerance to relative errors. So let's do that now. So for the volume, it's going to be 0.004, and for the weight, it's going to be 1.39 times 10 to the minus 6. Not surprisingly, the analytical balances error is much, much, much smaller than the graduated cylinders. Now you just divide the mass by the volume to get the density, and we have those numbers, and we then need to propagate the error. And by propagating, okay, so what you're going to do is you're going to sum the squares of the relative errors, and that's going to be how you get the total or propagated error. So the density is easy. It's just mass divided by volume, and then to get at the relative error, we're going to basically say it's the 0.004 squared plus 1.4 times 10 to the minus 6 squared. Take the square root, and that's now a relative error. And notice something very interesting. When you have errors that are different by more than 2 or 3 orders of magnitude, the one that's smaller in effect disappears, because really the error is now dominated by the least precise instrument. So error propagation can sometimes get really simple if one instrument has at least 2 orders of magnitude higher relative error than another. You're probably pretty safe in neglecting the more precise instrument and assume that your error is going to be dominated by the imprecise instrument. And this is kind of just a mathematical explanation for why that's true. So the answer that I would report would be 7.18 grams per mil. That's just the average. And I would do plus or minus 0.4%. If you convert back, take 0.4 times the 7.18, you can calculate the absolute error to be 0.03 grams per mil. Let's do another example. We got two more, and I'm going to just uncover these pretty quickly and talk through them. Feel free to try these examples yourself and then watch my work. So here we're given absolute errors, and I'm being asked what's the density. So it's very similar to last time. However, the difference is I don't have the volume. I'm going to have to derive the volume or how to calculate the volume of a cylinder from these dimensions. So let me show you what we do. Well, volume is just pi r squared L. So the density is just mass over volume. So you can see what we're going to have to do is calculate mass divided by pi r squared L. So again, we're going to have error in both the mass, the radius, and the length. And that's what we really care about in terms of propagation. So what we're going to do is calculate the relative error for mass, radius, and length, and that's what I did here. And what I did in the final expression is I actually included the plus minus relative errors in different color just so we could sort of see them. And those are the three errors that we're going to now propagate. So one thing you need to know is since you had an r squared, you're going to write it as r times L, which means you have to count the error on r 2 times. And when you do that, you're going to get a density error of about 0.0115 or 1.15% relative error. Now, what's interesting about this is in this case, all of our relative errors were about the same, so we couldn't really neglect any of them. They all contributed to the overall error in the density, which I reported out to be 0.102 in absolute numbers. So I would report 8.90 plus or minus 0.10 or 8.90 plus or minus 1.1%. Let's do another example. This is going to go real fast. So this is useful in terms of just practicing some solution conversion. So you made an ammonia solution by diluting a certain amount of volume of ammonia. So what's the uncertainty in the given molarity? So to do this, you have to know that it's just moles over volume. And to get the moles of ammonia, and I'll refer you back to the dimensional analysis lecture, you're going to take the concentration of ammonia, you're going to convert it to weight, and you're going to get the molarity that way, the moles that way, and you're going to divide the whole thing by the net volume. Each of those measurements has an error which was given in the problem. And what I've done is I've turned that error into basically absolute in most cases. Then the relative error is going to be this, because this is multiplication division, we're going to be summing the squares of the relative errors. When we do this, we get 1.878 estimated sig figs. But we don't want to report that many sig figs, so we're going to report out 0.247 molar. 1.87 is not a good choice. 1.88% is better. 1.9 would be even better. So make a note of that in your own notes. So I hope from these examples you've gotten some good case studies of error propagation. It's really simple to do. Just remember, if it's addition and subtraction, you can work with absolute errors, and you take the squares of all those errors, you sum them, and then you take the square root to get the propagated error. Or if it's multiplication division, you're going to be working with relative errors. Thanks so much. See you next time.